So let us take a look at how we can solve problem 618a. Note that the background noise is a lot smaller now due to the microphone that Peter lent me. It's quite useful. Thank you for that. Well, 618a. We're asked to write down a finite difference approximation of the problem that has a specific truncation error. So let us just write down the problem again. What do we want to solve? We want to solve double partial derivative of u with respect to x plus double partial derivative of u with respect to y. Equal to some known function f, which we will be given at some later point in time. And we want to solve this for x and y on the unit square. Where u of x comma y is equal to 0 on the boundary of the unit square. And what do we want? Well, we want to solve this using a finite difference approximation. We want to solve the problem using a finite difference approximation which has a certain error, and that error will also be something that determines which finite difference approximation we should use. With truncation error of big O, of big O of h squared plus big O of k squared, where this is our y step size and this is our our x step size. Now, in order to make some kind of finite difference approximation, we need to discretize our problem first. So, discretizing the problem, aka drawing a grid. Let's do that. Now recall that what we're interested in looking at is the unit square. Here. So we are interested in looking at the unit square d. 0 to 1, 0 to 1. So this is d. And what we want to do, according to the books section, a very good idea is to look at the book section 6.2. Basically, you can just proceed as the book does in section 6.2. Just do exactly what they do, and you are more or less home safe. Well, let's look at what they do in the book and just use the same notation as they do in the book. In the book, they label this x value as x0, and the last x value is x in plus 1, and then they call this value here y0, and then they call this over here y in plus 1, ym plus 1, sorry. So this is the y-axis and this is the x-axis, and each step size along the x-axis is h, and each step size along the y-axis is k. Now, what do we know? So we have boundary conditions, right? We have boundary conditions given. Hence, we know the value of, well, of what? We know the values of u in these points here, and in these points, and in these points, and in these points, because the exercise tells us that u is equal to 0 along these points. So which grid points are these exactly? Which indices do these points have? Well, they have to have some index numbers going that have something to do with 0 or n plus 1. So we know that for everything down here, aka for u, we know the values of u 0 comma j for all the j's going from let's see, yeah, we know, no, not down here, I'm getting confused as well. Let's see, 0, that's x0, this is this. Okay, so for u0 comma j, for all j's going from 0 to m plus 1. Great. J equals 0, m plus 1. And also we know the values up here, no, over here, which is un plus 1 comma j, again for all the j's going from 0 to m plus 1. And also we know the values of ui comma 0, which corresponds to all the values along this line here, for I going from 0 to n plus 1, and also ui comma n plus 1. No, not n plus 1, sorry, m plus 1, which is up here. So the values of all of these points, which are like here, 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 etc., all of this, according to the boundary condition, equals 0. So we know that. What else do we know? We know something about the bounds, and we know that we want to approximate this partial derivative and this partial derivative using a centered approximation. So when you want to do that, you want to consider formula 613, 614, and 615, right? And you want to consider the fact that in the book they solve this problem for f equals 0. So the right hand side of what you see in formula 613, 614, and 615 should be adapted to your problem accordingly. And notice what happens with the k squared. I don't know how much more I'm supposed to say now without just giving you the whole answer, but look at formula 6, 13, 14, and 15. I can tell you that the left hand side should stay just the same, more or less, as what's in the book. The only thing that you have to consider is the right hand side. So this should be something new. Yes, this should be something else than what you're seeing in the books 615 and 617 actually. It's so in order to find the finite difference approximation here, let me just write down, look at formula 613 to 617 in the book. Yeah. And then after these formulas in the book, they note the boundary conditions, but actually you already know the boundary conditions from down here, so now you have more or less your grid here, and you also have the finite difference approximations that you're supposed to use. So in the next video we will talk a little bit about what happens when we take our finite difference approximation, which will remind you very much of Formula 617. When we take that and try to translate it into a matrix system. So that will be part of the next video. So just start off with drawing a grid first. And do not underestimate the importance of drawing this grid, because when you program your problem, you will want to draw this grid as well.